Our next speaker in line is joining us from Data Stacks, wherein he works as a senior regional data architect for the APAC region. Prior to that, he has served similar roles with various tech companies, including Azure Systems and Xyrus. In his role at DataStax, he is focused on building awareness of DataStax offerings and supporting the Apache Cassandra community. His session today will focus on why the new types of databases are quickly becoming the leading choice in terms of addressing business needs of real-time data processing and supporting domain-based architectures. With that, I now hand over the frame to Mr. Yoshi Kimoto. Kimoto-san, over to you.
Hello, I'm Yoshi Kimoto, working for DataStax. I am the APAC Senior Regional Data Architect, which is a pre-sales role in DataStax. And DataStax is a company that is behind Apache Cassandra, which is a distributed, open source distributed database. I'll talk about a little bit on that, but basically the talk today is mainly about what I see as, which is coming in the very near future in the data layer. Basically, mainly about the database, but some things around it as well. So it's sort of like a sneak peek into what we'll be seeing, or maybe we are already seeing. And because I have a long span of history in the industry, like over 30 years, I've seen all of the evolution from the back in the day. So I'm going to start talking about that first and see, based on that, what is coming. Okay, so past and the present is what I'm going to talk about. The past, when we hear about databases or the data layer, what we usually had in mind is, well, basically when you hear databases, it's about collection of data or information, whether it's in a raw format or whether it's in a file kind of format, and anything that you are recording or you're looking at in a digital form. Basically, if it's a database, then you think is everything as an organized, structured. It may have a schema, sometimes it doesn't. But basically, when you think of databases in regular terms, you would think of it as a structural and organized manner. You would store it, you would retrieve it, you would modify it, you would delete. And there will be various access methods to that, and the database system will provide you with those access methods as well as ways of interacting with it and also managing it. And there are various kinds of programming languages that you would use to interact with the database, or access methods, maybe through libraries or maybe access drivers, and there may be some frameworks around that would be more of a layer up from the more primitive level of access. And of course, as I said, there's this management system that takes care of the database, just not for storing and retrieving, but also you need some backups. You might need to clone it for some other purposes. You might need to ETL it to some other places and all that kind of thing. So you would have a management overall for that. And most of the time, when we think of databases, it will be relational data. And it has been born like 50 years ago. It's quite a long time, but it's still a dominant type of database. So we have seen it evolve over the years, but when we think of database, generally we would think of it as a relational database. But then as time goes by and the way that we interact with data has changed over time. And this is brought by the internet. So everything is becoming distributed. It comes first with the distributed network, and then it comes with distributed compute, and now it's becoming distributed data. And internet has brought this about. So in the old days, you would have like things called UCP, which is Unix to Unix copy. Basically, it's more like a bucket relay of data between computers to forward all the information that you have to the other computers to share information. And there would be bulletin board systems where you have a huge server farm and you would access there to look at data or information. And that was sort of the beginning of how you would interact with the other people in the world. But then ARPANET, experimental kind of network that was first run in the US with the government and also universities, which eventually evolved into the internet. So, and then after that, there came a time where things like Gopher came about and you would start to share files. Then there was like NFS, and then came the World Wide Web. So people started to connect information that resided on their servers and specifying a specific URL, you would be able to access other data around the world. And then usually you would be logging in or calling the places where you had those information or calling each other. You would have modems that you would connect to each other, and then you would have your own telephone lines eventually that will be connected all the time. And then came the internet service providers and web portals where you would find the information, you'll be able to search for information. So all of this brings about immense amount of data, and the expectation that you will always be able to access the data around the world, and you would have a global reach, and also with a very low latency if you're even half aware around the world. Nowadays, it's much faster than before, because we have very thick lines between continents and mostly fiber-based and many of those fiber-based lines. So in terms of the internet, the world has become smaller and faster, but the data is growing more and more. So with all this kind of environment, the databases had to evolve, right? So to cater to these requirements, I mean, the requirements were that you would need to be able to handle immense amount of data. And the expectation of a database is that it's always on. You would access the data any time of the day, and you won't expect to have a downtime. Also, you would want to have access to the data from anywhere of the world with low latency. So that was the requirements that the databases needed to handle. And in order to do that, technically, you would have to the implementation was to have a horizontal scalability, meaning that you could add on nodes to expand your capacity, whether it's for the workload or whether it's for the amount of data. And of course, you could expand in a global manner from one continent to the other. And while you do that, you would also want to be fault tolerant, meaning that you would have the redundancy of compute as well as data, which means that you would have replications. And even if one compute is down, you could still access data with using another compute, and you would have replication of the data in other places so that you could use the data there. And that is basically what the new requirements were. And those are the basis for the new type of database that emerged. Right? So when you think back and the types of the data, the places where the data are residing, you would have these types of operational data layers and analytical data layers. For example, for the original, might brand it as legacy or classic, you have the relation databases, which is more of an operations. And then you'd have the data warehouse types of data layers like Teradata and Netezza, which would handle more of the analytical kind of workloads. But as the internet grew and the amount of data grew, and the expectation for the connectivity and all the requirements along with that came around, there were new types of databases that were developed and new types of data layers that were developed, like the likes of the NoSQL databases like Cassandra, Redis, Mongo, and all those sort of things. And nowadays, I think apart from NoSQL, there's NewSQL, more of the relation types of databases, but with more scalability. And also from the data warehouse perspective, there's more things like distributed analytical handling workload like Hadoop or Spark, or nowadays like Snowflake and those kind of things. So the requirements change as the internet came along, and the expectations for the data layer has changed along with that.